Hello, this is Harrison Moore, and this is Lab 2 for Physics 2211. So, in this lab, our purpose was to compare position versus time graphs of real world experimental projectile motion, then compare this to a computer simulated version with and without drag to show the effects on projectile motion. Some of the fundamental principles we ran into while doing this lab was first, Newton's second law: the acceleration of an object depends on its mass and the amount of force applied, or better known as F equals ma. The velocity update formula, which is velocity final equals velocity initial plus F net over mass times delta time. The position update formula, which is position final equals position initial plus velocity times change in time. And then force of gravity and drag, F grav equals mg, and drag equals b times v squared times joules. No drag equal means that F net equals F grav because that's the only force acting on the system. So in our tracker video, which I will show you right now, showed it twice. We threw a paper ball and let F grav and F drag do work on the paper ball until it hit the ground. I used this video and tracker to create a table and then a graph showing position. The video is again, just so you can see it one last time. Okay, so now assumptions for the computational model. In the computational model, gravity and drag are the only forces acting on the system, and all tracker markings are at the absolute center of the object. So here's my code. On the left, you can see without drag, and my b equals 0. That is important because that is the value of drag. So down here in this, the f drag equals 0 because b equals 0. That is important because that means F grav is the only force acting on the system. So you're only going to have gravity. On the other hand, on the right here, we have b equals 0.0041. So that was the constant I found for drag. And when you plug it into this equation down here, you have F grav, obviously, and then F drag actually produces a number now. So then F net equals F grav plus F drag. So this means that you're going to have two forces acting on the object, whereas in the first one, since F drag equals 0, it was just F net equals F grav, which we stated earlier. So here are my graphs from GlowScript for the forces of just gravity. As you can see, X is in a straight line because there's no forces acting on the X. It's only acting on the Y. As you can see here, this is the force of gravity making it go down. And then this down here is the trajectory of the object, Y position versus X position. So now, with the gravity and the drag, this position graph has a slight bend to it. It's you can't see it to the eye, but there is a little bend to it because there are forces acting in the X direction. And then obviously you have both. You have Y, but you now have two forces in the Y direction. So our graphs do look a little bit different, and you'll see that when I plot them on a graph altogether. So here are possible sources of error. Differences of placing center of mass and tracker, errors in determining drag coefficient, and finally, there might have been some other forces like AC or wind acting the system, and that's really, really hard to eliminate, especially in a situation like this, unless you're in a perfect environment, and we were not. We just filmed it in the hall next to our lab. Sorry, I skipped this one. Here's my graph. I just want to make sure I show this. So as you can see here, the blue is a tracker video, and that's the line's not perfect just because, like I said, sometimes the tracker wasn't always put in the exact center of the object. It's really, really hard to do that perfectly. You can see that line right there. And then the red line is the no drag. The only force is FG. So it reaches the ground a little bit quicker. Whereas the yellow, where you do have drag, it reaches a little bit slower because as the mass is going down, the drag is pushing against it, making it reach the ground slower. Here. And then by conclusion, what does this mean? So the definition of terminal velocity is when a free-falling object has zero net force acting on it. Since ours was about a second video, it did not have enough time or height to reach terminal velocity. If we were to do that, we would have had to have dropped our object off of a very tall building and let it fall for multiple seconds to get to where F drag is equal to F grav. That's how F net would be 0. And then what if So the ball would reach the ground in more time because the drag acting on the ball would only be in the y direction and would have no magnitude in the x direction. So this would make it where the force of drag is only pointing up, so it's only counteracting F gravity. Instead, it was only a piece of the vector that was acting against it because there was magnitude in the x direction. So this would make the ball take more time to reach the ground. Ultimately, it would be a very marginal difference, though. It would be a very small difference in time, especially in a very short time span like we saw in our experiment.